In this video, we're going to be looking at an old paper for demonstrate understanding of atoms and radioactivity. So this is a 2009 paper, and as such, it doesn't cover everything that you might be asked to do in your assessment for the new version of this standard, which is 91172. In particular, this paper won't cover any aspect of mass being converted into energy according to the formula E equals mc squared. So you might want to do a little bit of practice on that as well. I'll put a link in the description to take you to this paper, and it would be a really good idea if you had a look at the paper first, tried answering the questions, and then watched the video just to help you along the way. So question 1 deals with different models of the atom, and we're asked to describe one aspect of Dalton's model of the atom. And Dalton suggested that all matter was made up of these indivisible particles called atoms, from the Greek atomos, which I believe means indivisible. And these particles that everything was made of would be pieced together to make up matter. The atoms for each element were unique, so the atom for hydrogen was different to that of oxygen. And so our answer might look something like, Dalton suggested that all matter is made up of tiny indivisible building blocks called atoms, and atoms of each element are unique. Now, we often talk about Thomson's model of the atom as well, and that's the one that's described as the plum pudding model. And so in the plum pudding model, Thomson described a sea or a sphere of positive charge with negative corpuscles, which was the term he used until we developed the term electrons. And so these negative corpuscles, or negative charges, were interspersed in that positive sphere. And the overall charge was neutral because there was an equal amount of negative and positive charge. The describe in question A would make that one an achieved level response. In B, it's describe again, but if you go on to talk about the overall charge being neutral, then that would get you a merit. Another famous experiment that's really important to this standard and this topic is Rutherford's gold foil experiment. And what we see in this diagram is the source of radiation inside a container with one opening so that the radiation could be directed towards the gold foil. The source that was used was an alpha emitter, so alpha particles are emitted along this line, and when those alpha particles interacted with the gold foil, then some quite interesting results were found. So we're asked to give the purpose of different parts of the experiment, and the first one is the zinc sulfide fluorescent coating on the screen. So alpha particles, when traveling through a vacuum, are invisible, and without the zinc sulfide screen, you wouldn't see any effect of the alpha particles. So when the alpha particles hit the zinc sulfide screen, there is a reaction and a flash of light is given off. So the zinc sulfide screen would glow or flash every time an alpha particle hit it, and that would allow you to count the alpha radiation and also to locate where the alpha particles were traveling to after interacting with the gold foil. So alpha particles are invisible to the naked eye, but they create small flashes of light when striking the zinc sulfide coating, which allows them to be counted and located. Why was the shape of the screen circular? Well, it needed to be circular so that the alpha particles could be detected when they came off in any direction. The grade for question C involves 3 parts, and we'll look at the third part now. So what was the purpose of the evacuated chamber? The evacuated chamber, as stated in the question up here, is a vacuum, and that means that there is no air or gas particles inside the whole chamber. And the reason that it had to be evacuated is that the alpha particles could be deviated or ionized with air particles before they interacted with the gold foil. And so the chamber had to be evacuated in order for all of the alpha radiation to be accounted for. What I mean by that is if the alpha particles had interacted with the air beforehand, then they would strip electrons from the air, given that alpha particles are a helium nucleus. So that's 2 protons and 2 neutrons. They've got a positive charge, and that positive charge could pull the electrons from other atoms or molecules in air, which would then turn the helium nucleus, the alpha particle, into helium gas, which wouldn't react with the gold foil and wouldn't be observed with those flashes of light. So our answer might say, the chamber had to be a vacuum to prevent alpha particles from ionizing with air. Stripping electrons from air would turn alpha particles into helium atoms that would not react with the zinc sulfide screen, so couldn't be detected. Now, those 3 answers combined would give up to an excellent. So you'd be looking for, if you'd done 1 of them well, achieved, 2 for merit, 3 for excellence. That brings us to question 2. And so this is a step further from the experiment. We're now looking at the gold foil. Gold is very malleable, which means it can be hammered into extremely thin sheets. And we believe that the foil used by Rutherford was only about 3 atoms of gold thick, so incredibly thin. We've got the beam of alpha particles coming from the left to the right, and we can see that occasionally some of those particles are deflected at small angles, and even more rarely particles are deflected backwards from the gold foil. And it was these observations that helped Rutherford to understand what the model of the atom must be. So he made 3 conclusions based on these observations. Now, the first one I'll mention is that because the majority of the alpha particles passed straight through without being deviated in any direction or being bounced back, then they weren't interacting with anything the vast majority of the time they passed through the gold foil. And what that told Rutherford was that the atom must be mostly empty space. Now, occasionally some of those alpha particles, as they were traveling through, would be deviated by small angles. And that told Rutherford that there must be, given that most of the atom was empty space, there must be small regions in the atom that had charge. And those charged regions would deviate the charged alpha particles. And the third point would come from the deflected particles. So when the particles very rarely sort of bounced backwards, then that led to the third conclusion. And the third conclusion was that if the alpha particle bounced backwards, then in order for it to do that, it must have hit something much more massive than itself. Because in any collision, if the particles in a collision were of equal mass, then you would expect both of them to be deflected. But the particles inside the gold foil didn't seem to be deflected. It was the alpha particles that were bouncing back that suggests that the alpha particles were much, much lower in mass than whatever it was they were hitting. And so that told Rutherford that there must be these small regions inside the nucleus in order for the particle to be deflected backwards, they must be the same charge as the alpha particle. And in order for the alpha particle to bounce back, he also expected that the mass of those regions inside the gold foil must be very, 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 very massive compared to the alpha particles. And you could also describe this as the areas that were identified in the gold foil as being very, very dense. So the few alpha particles that bounce backwards suggested the small regions of charge in the gold foil must have far more mass than the alpha particles. And if you explained correctly these three conclusions, then that would be an excellence level response. Okay, later in question 2, we are discussing some other work carried out by Rutherford, so firing alpha particles into a jar of nitrogen gas, and he found that oxygen was created and one other particle. And so we're asked to write a nuclear equation for the reaction. So we're going to be starting off on the left-hand side with the nitrogen, and because alpha particles were fired into the jar, that's going to be on the left-hand side as well. So we've got alpha particles, and you could draw that as an HE with a mass number of 4 and an atomic number of 2, or you could use the symbol for alpha and use the mass number 4 and atomic number 2 as well. We're adding that to nitrogen, and then we're going to draw an arrow. You've got to be very clear that you're using an arrow, not an equal sign for these equations. And we know that oxygen is created, and so on the right-hand side of the reaction, we would have oxygen, mass number 17, atomic number 8, and that leaves one other particle that we need to identify. So this is our equation, and here's the alpha particle that I mentioned, here's our nitrogen, and the oxygen. So that's all information that we've got from the question. Now, there's one other particle, and at the moment we might not know what this is, but to get to this particle, we use the mass numbers, so the 4 and the 14, and we know that the total mass number on both sides of the reaction has to be kept the same. So 14 plus 4 is 18, which means that 17 plus a number must be 18 as well. So that tells us this number here is going to be 1. We use a similar principle for the atomic number. So atomic number 2, atomic number 7 totals 9, and we've got 8 over here, which means we must be adding 1 to it so that the atomic numbers on both sides of the reaction add up to the same amount. So that gives us mass number 1, atomic number 1, and if the atomic number is 1 and the mass number is 1, then that tells us that it is just a single proton. And a single proton is the nucleus of most hydrogen atoms. And so we could identify this as hydrogen. So name the other particle that was produced as a result. Well, that's a proton or hydrogen nucleus. And the two conservation laws that were used in order to write our equation were the conservation of mass number and the conservation of atomic number. We would be looking at a merit for getting the equation correct, and then we'd be looking at an achieved for identifying that unknown particle, and D would be achieved as well for getting both of those correct. In part E, we're asked to identify two types of radiation, and there's quite often a question based on this concept in an exam, so you should be ready to discuss the different types of radiation based on their penetrating powers. So P from the radioactive source, we can see doesn't go beyond the paper. So whatever P is, it's being stopped by paper. And you should know that alpha radiation has a relatively weak penetrating power and would not penetrate paper. The alpha particles would be ionized on contact with the paper and would not move beyond the paper. So we should know from that that P is an alpha particle, or alpha radiation as it's being stopped by the paper. Beta radiation we would expect to penetrate aluminium foil to some extent if the aluminium foil was relatively thin, but beta would absolutely not penetrate 2 centimeters thickness of lead. And so the fact that Q has moved beyond the lead tells us that Q must be gamma, gamma being the type of radiation that has the greatest penetration. And for identifying both of those, we will be looking at merit. So Q must be gamma as it penetrates lead. Okay, on to half-life. And we've been given a number of chemical elements here and their symbols with their atomic numbers. And we're told that plutonium-241, which has a half-life of 14 years, is a typical product from a nuclear reactor, and it decays into americium-241. So we're asked to write a nuclear equation for the decay of plutonium-241 into americium-241. So we would start off with plutonium-241, and we know from the 241 that the mass number is staying the same. So whatever type of radiation is being released cannot change the mass number. If alpha particles were being released, then we know that their mass number is 4, and so we can't be dealing with any sort of alpha decay here. It's possible that there's gamma radiation, because gamma radiation wouldn't change the atomic or mass number. And we also, if we were considering beta decay, would have some idea that when beta decay occurs, we're looking at a neutron inside the nucleus decaying into, or turning into, splitting into, if you like, a fast-moving electron which is ejected, and a proton. And because we're losing one neutron but we're gaining one proton in the nucleus, then the mass number stays the same. And so for our nuclear equation for the decay of plutonium to americium-241, we're probably looking at beta decay in this situation. And so we can write out our plutonium. 241 is the mass number, 94 is the atomic number, which we get from the question. We've got an arrow, remember an arrow, not an equal sign, going to the americium-241 with atomic number 95, again from the question, plus a beta particle, so I've used the beta symbol here. I could also use a lowercase e for the electron, mass number 0, atomic number -1. And that follows the law of conservation of mass number and the law of conservation of charge, of atomic number, sorry. Okay, so in question B, we're asked to draw a graph to show the decay of 32 grams of plutonium-241, and then we're going to use the graph to find the mass of plutonium after 20 years. We've got graph paper provided, mass in grams on the y-axis, and time in years on the x-axis. With 32 grams of plutonium as our starting amount, and given that we've got these 4 boxes each subdivided into 10 smaller boxes, it's probably going to make sense to go up in tens on our scale for mass, so 0, 10, 20, 30 up there. And for our scale, our time scale, we know we're going to have to use the graph to find the mass of plutonium after 20 years, but knowing how half-lives work, we're probably going to want more than 20 years to be able to show what's going on with the change in plutonium over a long time. And so I would suggest that we use 0, 10, 20, 30, 40 as our scale on the time axis. We know that at time 0, we're going to have 32 grams of plutonium, so we can plot that on the graph here. And then, given that the half-life of plutonium was 14 years, then we know that after 14 years, we're going to have half of that 32 grams, which would be 16 grams. So we can plot that. 14 years on from that, there's going to be half of 16, which would be 8. And that's over here. So that was 14 years. And then another 14 would be 28. And the mass has halved from 16 to 8. And then we could plot another one beyond that. So we're going to go from 8 to 4 in another 14 years, which takes us to 42, and we've plotted that point here. We'd use a smooth line of best fit to draw the relationship here, and so that's going to look something like that. And then what we can do is we can, after 20 years, we can draw a line going up from 20 to see where it intersects our line of best fit, and then draw that line along to the mass axis, and we can see that that value is about 12 grams. So after 20 years, we expect there to be about 12 grams of plutonium-241 remaining. And that is an excellence level question. Okay, americium-241 has a half-life of 432 years. It's widely used in smoke detectors. It emits alpha particles and gamma radiation. So we're asked to describe and explain the changes inside the nucleus of americium-241 when it emits an alpha particle and a gamma ray. Okay, so the change with the alpha particle is the emission of the helium nucleus. Again, that's 2 protons and 2 neutrons. And so the mass number of the americium-241 would drop by 4, and its atomic number would drop by 2. Now, when the gamma ray is emitted, there's no change to mass number, no change to atomic number. We're just losing energy in the form of a gamma wave. And so both the emission of an alpha particle and gamma ray help to stabilize the nucleus, but the gamma ray doesn't reduce the mass number or atomic number. And a full and complete answer there involving the changes of an alpha particle and the reasoning for the changes inside the nucleus when an alpha particle is emitted, along with the lack of change to the nuclear structure when a gamma ray is emitted, but also identifying that energy is lost with the gamma ray, and that those changes make the nucleus more stable would give you excellence. And the last question of the paper, 3D, asks us to write a nuclear equation for the decay of americium-241 when it emits an alpha particle. And so we're going to start off with americium-241, and we can see if we flick back the page that the atomic number of americium was 95. We're told it emits an alpha particle, so we're going to then draw an arrow, and we can write in the alpha particle. We should know that the alpha particle can be represented by the alpha symbol or an He for helium, mass number 4, atomic number 2. Now, we wouldn't be expected to know this, but we should be able to work it out by deducting 4 from 241 to give us 237 as the mass number of our unknown particle, and then deducting 2 from 95 to give us 93. And if we flick back to the previous page, we can see that if we take 2 away from 95, we've got 93, and that's Np, which is neptunium. And so coming back to our question here, we've got, we can identify that particle after the decay, alpha decay of americium, is neptunium. And for that answer, we'd be looking at an achieved. Okay, I hope that was helpful for you. If you've got any questions, feel free to post them below.